when you're looking at Calculus 1 content, what we study for the most part is things such as we're talking about limits, we're talking about derivatives. And again, we also talk about the tangent line, which is connected up with the limits and with the derivatives, and also some different applications thereof. We looked at different ways of how you take a derivative. We talked about the power rule. We talked about looking at trigonometric functions. We talked about even inverse trigonometric functions, which we were able to determine the derivative, but we had to go about it through an implicit differentiation procedure. We talked about logarithmic differentiation. So all different types of ways of how you take derivatives is something you want to make sure you're pretty okay with how to do it if you have to do it. So also product rule, quotient rule, and in particular, the chain rule is very, very important. Okay. And then from here, we did start venturing a little bit into this whole entire idea of integration. When you start jumping into Calculus 2 concepts, you can take Calculus 2 and you can really divide it into 3 different pieces. First off, we do look at integration, but we take it to the next level. We start looking at techniques of integration. What are you going to do when certain procedures, when they fail? And how can I know something's going to fail before I decide to invest a lot of time using one procedure? And we're going to look at different characteristics within the integrand to try to help us figure this out. And then the next thing is we're going to do something called your sequences and series. And this is a really, really fun topic. It's looking at series, you've seen them before, but they're going to be a little bit different from what you maybe have seen before. And then towards the end of the course, we're going to get something called your parametric equations. And this is a great segue here into Calculus 3. In particular, look at something called polar coordinates. So for the most part, here are the 3 breakdowns for this course. Techniques of integration, this will go on for about 5, 6-ish weeks. Same thing here, and a few weeks down here at the very end, we get into the parametrics. Okay? Now, as we get into the parametrics, it is going to get a little bit easier, but there's a lot of heavy lifting right here, especially with integration and with series, so you definitely want to stay on top of it. You don't want to get behind. Okay? Well, taking it back again to the good old days of Calculus 1, we looked at integration. Integration, we saw it in various different applications. And one application is whenever you have some kind of curve, maybe out in space, and what you want to do is find the area under the curve. Well, how can we go about this? Well, one approach that you can possibly take if you want to find the area under the curve is you can start packing it with certain objects. And what you can possibly do is you can pack it full of circles. Could you not? Could you not put a bunch of circles under the curve? And then if I figure out the area of all the circles, then I can get an approximation of the area under the curve. It's like taking maybe a flask or a beaker and it's full of water, and you maybe start pulling some pebbles into it. You try to get all the water made to come out, and then you measure maybe the pebbles to figure out the volume. Yeah, you can do things like that. Yeah, I can do this, but it starts getting a little bit cumbersome very, very quickly. Because if I have a circle here and a circle there, what about a circle there? And then I got to zoom in a little closer and say, okay, what about a circle right there, and try filling the gaps. Just like if you're putting rocks inside of a flask or a beaker, you can also put sand inside of it. And then you put more like refined sand you would put inside of it. So as you get smaller and smaller and smaller, you fill in more of the gaps and fill in more of the details. Okay, that does work. But again, what we want to do is think like a scientist, think like an engineer. It works, but what can I do to improve performance to make this better, more efficient? And the problem here is I have to think about the sizes that I'm going to need. So we say, okay, what can I do to make it more systematic then? Something that's a little bit more mechanical. And an approach that you can possibly take is instead of using circles, you can use triangles. Why could you not? If I use a triangle, I fit it a little better. I no longer have those gaps. But again, I got the problem of trying to figure out what's the size of the next triangle. I'm going to put here and here. Should I use isosceles triangles? Should I use right triangles? Obtuse? What kind of triangle should I use? So again, I still have the issue of it works, but I want something that's going to be better still. And as you keep digging into the question a little bit more on how to refine it, how to manufacture it, how to make it better, something that's more systematic, so you don't have to put a lot of thought into it, you realize what you need is something that has nice congruent shapes. And one of the nice congruent shapes that we can potentially use is we can use rectangles. And we looked at various schemes. One such scheme is use what's called the left-hand rule. Because you're using the left hand, the rectangle, which corresponds to the height of the rectangle, which is right on the function, right up there. If I talk about the right-hand rule, then I use rectangles whose right-hand vertex resides right on the curve. And I also have other things I can also do. I can talk about maybe a midpoint rule, but I don't have to just do left and right and midpoint. I can take a rectangle and I can maybe bump it off just a little bit. It's possible. Guys, think outside the box. Literally, this is a box, right? You don't have to be confined to the box, to the left, to the right, to the middle. You can do whatever you want to do. Start piecing it all together. But in order to do what you want to do, start piecing things together, you have to know how things work. How could you design some kind of system, some kind of program, some kind of machine if you don't know how it works? How could you start designing it virtually? That's what math is. You're designing things virtually if you don't know how the math works. Well, this is a pretty good idea where we could take a region and we can start chopping it up. But how should I chop it up? Well, one thing that we can potentially do is we can say, I just want to choose this region and this region as my rectangles. Completely possible. But again, that is foregoing what we said. We want some nice congruent shape, something that's a little more systematic, something I don't have to worry about and put a lot of thought into the process. So a lot of times what we want to do is make things uniform. Instead of having a very large width and a very smaller width and another rectangle, let's make them all the same. So I'll take the region from A to B, look at the length of the interval, partition it up, chop it up into maybe n equal pieces, and typically we call this delta x. Okay. Then the widths are all exactly the same for all the rectangles. Next thing is, what scheme do you want to do? Left hand, right hand, midpoint, or some other rule? And based upon what's going to happen, you're going to set this up one way or another. And we know that sometimes the shape of the curve, due to concavity, where it's going to be increasing, you might get an over approximation or an under approximation, based upon if you use left-hand rule, right-hand rule, based upon the shape of the curve, the concavity of it. But again, if I'm using left hand, create all these rectangles whose left hand is on the curve. And then I look at all these rectangles. Maybe if I want to find the area for this one, well, I know what the area of a rectangle is. The length times the width, and the widths are all delta x. So I got to figure out what's the height, this length up here. Well, what we do is we start off, we might say something like x naught. And then the next term, x1, then x2, then x3, x4, x5, and then maybe x6 if that's where you're stopping, or x to the n. If you want to go from here to there, to x1, you travel a distance called delta x. So in other words, x1 something more than x naught plus delta x. And if you want to go to x2, well, you're looking at x naught, and then you went not just 1, but you went 2 delta x's. And then so on and so forth. You go to x3, you travel 3 delta x's. And usually about this stage, you see a pattern that's starting to emerge. See, again, guys, math is not really about learning how to do calculations and how to do arithmetic. That's something completely else. What we're trying to do here is we're trying to understand how things work, how to put things together. We're trying to identify patterns, trying to recognize it, trying to understand the world that we live in. And here, I'm starting to see a pattern is starting to emerge, which I can inductively state. I have 1, 1, 2, 2, 3, and 3. So if I want to get a nice equation, it seems to suggest then that x sub k is nothing more than the very first term, then k times delta x. And that's how I can find the height, or the values for x, if I was to chop this up into uniform pieces using the delta x. And if I want to find the heights of the rectangles, since I am putting the rectangle right on the curve, I would take the function evaluation at maybe x1 get the corresponding y value, and that's the height. And there it is. For the next one, I would do the same thing. Take the function, evaluate it at x2, since I'm using the left-hand rule. If I was using the right-hand rule, then I would use the right-hand side of the rectangle. And then so on and so forth. Well, then that's going to say that you take f, evaluate it at x sub k times delta x. And what we have here is we have the area of the kth rectangle. And what we would like to do is take the area for the first one, and then for the second one, and for the third rectangle, put them all together. The way we put them all together, you can talk about a summation. And based upon if it's left hand, right hand, this value down here is going to change a little bit. If it's left hand, it starts off at 0, then 1, 2, 3, 4, and it doesn't include the right hand over here, it stops at 5. If it's right hand, then it starts off at 1, since it's using the right hand vertex. Then it goes 2, 3, 4, 5, and then also the 6. So if it's right hand, k is 1, and the upper bound up here is n. And what this does is it gives us an approximation. Well, that's great, but I want the approximation to be better and keep refining it over and over and over again. It has a lot of jagged edges, and if I was to fit it better with those congruent shapes which fit the curve better, it seems to reason then I would get a better approximation. And that is really a groundbreaking discovery that's very, very obvious when you really start thinking about it. To fit the curve better, I get better approximation. But to fit the curve better, I got to use smaller rectangles. Well, I want to not just do this once or twice. I want to get something that's going to be spot on, 100% exact, and not an approximation. So I want to keep refining the approximation over and over again. And as soon as I say something of the form of, I want to keep refining something, I'm talking about really no ends to it. I'm really invoking this whole entire idea of a limit as n races off towards positive infinity. Keep refining it, and then eventually the approximation is going to become exact. You take this, you take the limit, you take the approximation, and what you get is exact. Now, the way that we solve this back in Calculus 1, we did this whole entire idea of Riemann sums for a while. And we're really wondering, is this really what calculus is all about? Riemann sums? I don't want to keep doing this forever. If I do Riemann sums, I'm going to change my major. This is crazy. That was called math hazing. You had to do it because we had to do it. I don't know. But eventually, this started going away, and it brings up the whole entire idea of integration, where you have something of that particular form. And this really opened the doors to a lot of really interesting ideas. What integration can be used for? Well, when we're looking at the integral, there's various pieces we need to make sure we're well familiar with. The little f, we typically refer to that as the integrand. Over here, we refer to this as the antiderivative. And if you want, you can also refer to capital F as just being simply the antiderivative, because we typically would then say C is just going to be the constant of integration. And of course, we would have our integral symbol right there. But when you look at the integral symbol, what is it really? It's an elongated S. S for what? Superman? Nope. But it does sometimes go up, up, and away. S for sum. Why is that? Well, what's it saying? You can consider integration as being nothing more than a combination. You're combining things, putting things together, joining them. That's what integration is. You know, we use the word integration a lot outside the scope of mathematics. Integrate the workforce, integrate the school systems. That doesn't mean everyone's doing calculus. I think they should. But integration is not really an idea that is only reserved in a calculus class. And when you understand that, things really start falling in together a little bit easier, because integration is nothing more than combining things together. Now, as we progress, we'll look at different ideas of integration. We'll look at how to put things together, and it's all based upon the concepts of integration. But one of the things that we also did look at with integration is the relationships between the integrand and the antiderivative. So if I take the derivative of the antiderivative, you're right back to where you started, f of x. Okay, well, this is actually kind of groundbreaking, because it kind of reveals how we can actually do some integration. If I want to integrate x dx, I'm really asking, I'm thinking of this magical function. Read my mind. I'm not going to tell you what the function is, but I'll tell you what it does. If you were to take its corresponding derivative, you would get this function right here, f of x. In this case, x. What am I thinking about? Well, actually, there's a lot of functions I could be thinking about. One function I can possibly be thinking about is x squared over 2. That would work, but it's not the only one. I can also say plus 1. Because what happens when you take the derivative of x squared over 2 plus 1? Well, this piece definitely goes here. But when you take the derivative of a constant, what happens? Derivative measures rate of change. Constants don't change. 0. And I can keep playing this game. I can say 4. I can say 41. I can even say 373. A great prime number. It's a palindrome. Love it. But what we typically say here is we say plus c. And this is what's known as our indefinite integral. I don't know what's going on. I don't know what it is. Is it 1? Is it 2? I don't know. I'm indefinite. I'm not for sure, definitely sure what's going to happen. Whereas with the other integral we looked at, if I say from 0 to 2 x dx, I am definitely sure what's happening here because I have extra information with the endpoints. Well, in this particular case, when I have this type of integral, the definite type, we typically chase this back to the whole entire fundamental theorem of calculus. And if something says fundamental, it seems one of those things you probably want to know. It seems it's probably fundamental. So the fundamental theorem of calculus, we're looking at definite integrals. I look at the function little f. I'm still trying to find its antiderivative, and I can do the evaluation. I drop in the b, I drop in the a, I get my value out of it. So I would do the same thing over here. I'll drop in my b, or I drop in my a after I find the antiderivative. And one way of how I can express this, I can use a vertical bar, which is indicating that we're dropping the 2, dropping the 0. We get 4 over 2. Divides out to 2, and then subtract it off 0, and we get 2. And there's the answer. Okay, but again, this is a definite integral. And one of the applications we have for definite integrals, there's a lot of different applications, but one of the applications we just looked at, when I keep looking at the Riemann sums, looking at the rectangles under the curve, if I keep adding up those rectangles, I eventually came up with this idea, and we're motivated again to try to find the area under the curve. The approximations eventually become exact. I just keep refining the approximation over and over and over again. So one way of how I can interpret this is that's nothing more than the area under the curve. What's the curve? It's x. What does that curve look like? It's a line. It forms a 45 with a horizontal. Goes from 0 to 2. And what I just discovered was, roundabout way, the area of that triangle. That's how I can use integration. Okay, so if this is y equals x, point up here is going to be 2, 2. Base times height divided by 2. Lo and behold, I get the same thing. Okay, so what that tells us, it tells us a lot of information. It gives us also another way of how we can approach integration at times. Interesting. So if I want to integrate geometrically, let's say if I have the integral from 0 to 1, and just start off, let's say we have 2x plus 1, we have our dx. Now, the dx, before I forget, that's talking about the variable of integration, what you're integrating with respect to. It seems very insignificant, but it's not. You really do need to have that in the problem. It's like saying, and that's it. You missed the whole entire sentence, right? Because I left something off. You didn't know what I was talking about. So you really need that dx to know what you're talking about. It becomes a lot more important, let's say, as you progress and you get to the calculus 3, you realize something that seems so insignificant at the moment means a whole lot later on. It's like a cornerstone, maybe in a problem. Okay, but anyways, we can go through the whole entire integration process where we could take this integral and we can split this up. We integrate the 2x. We use what's called the linearity of integration. If I have two functions, maybe like g and f, we integrate. We split it up like such. So you integrate the 2x, we apply the power rule of integration. And the power rule of integration, as you might recall, two pieces to it. The first piece is, we say x to the power of n plus 1 divided by n plus 1, only when n is not -1. In the event when n does equal -1, you're going to get the natural log of x. Now, it's just not natural log of x, but it's absolute value. Don't forget the absolute value. If you're working a homework problem, you're throwing into an online math assignment, you're getting it wrong, it might be the case that you forgot the absolute values. If you put parentheses around it, you might be getting it wrong. Go back and double check that. Now, the reason why it's going to be the natural log of x, look at the relationships again between the integrand and the antiderivative. If you take the derivative of your antiderivative, you're right back to the integrand. If you take the derivative, natural log of x, what do you get? Take the argument, put in the denominator, up top, put its derivative, you get 1 over x, which is just another way of saying x to the minus 1. So when you integrate 1 over x or x to the minus 1, you are going to pick up the natural log. Well, we use this property, change everything over. We'll have x squared plus x, because when you integrate 1, what's the derivative for something that's going to get you, the 1? The derivative of x is 1. That's why we're going to get to that value. So I can also write in terms of just integral dx, or if I want to, I can say integral 1 times dx. They mean the same thing, but we are going to get this x and then plus c. Now, because we are really talking about a definite integral, not indefinite, I don't have to worry about the plus c. I only worry about the plus c when I have that, I don't know what kind of integral it is, the whole entire indefinite case. So here I can do the evaluation from 0 to 1. Take everything, drop it in, 1 squared plus 1, subtract it off, 0 squared plus 0, and in the end we get a value of 2. Okay, so that's how we do this algebraically. Suppose that the question asks us to do it geometrically. How can we go about it from that procedure, that approach? Well, to do it geometrically, the first thing I want to do is identify what the curve is I'm actually talking about. Yank it out. You're looking at 2x plus 1. Sketch it out. What does it look like? Looks like something like that. Look at the endpoints. We're going from 0 to 1. And if we're going from 0 to 1, that means we're talking about this region here. So I'm looking at a trapezoid. Well, I can either remember the whole entire formula for a trapezoid, and if we forgot it, it's not a big deal because we know how to put things back together again. A trapezoid is really nothing more than a triangle on top of a rectangle, or maybe some kind of square, I guess. Well, right here, we're going to look at the point 0, plug it in, 1. We got the unit square, unit box. And up top, we're going to be looking at, plug in 1, we get a value of 3. Okay, so there's just lots of different ways of how we can approach this problem. You can look at it in terms of a trapezoid, a square, a triangle, or you can look at the bigger triangle and just chop this piece off. There's more than one way of how I can work this problem. Okay, but you just keep cranking this out. You would have the base, you have the height for the box, and then for the triangle, 1/2 times the base times the height. The base is going to correspond to 1. And then the height, if this is 3, and you're chopping this piece off, how much are you removing? Yeah, so you're left with 2 here. And here comes the question. What's 1 plus 1? I don't know, it kind of depends, I guess. But in this class, 1 plus 1 is going to be usually 2. Look at that. We get 2. Well, let's crank this up a little bit more, make it a little bit more challenging. That seemed like that was a little bit too easy. Okay, now it's possible to do this algebraically. We're not quite there yet, but we will be there pretty soon in the upcoming weeks of how we can do this. But I can also do this geometrically. The first thing is I want to identify what the curve is we're actually talking about. Yank it out. What is that? Well, I see a square root, so I guess that means it's going to be like this. Or does it mean it's going to be like this? See, what I'm doing when I'm saying this right here, I'm guessing, aren't I? I guess that's what it means. Guess it means this. Well, in mathematics, we don't really want to guess. We want to be certain of what it is. When you look at the problem, what's the first thing that comes to your mind and says, nope, I'm going back to bed. This looks bad. To me, it's that radical. I don't really like radicals. Math or in life, I guess, but what can I do to a radical? What's a radical afraid of? Being a square. Don't be square. You know, don't tread on my radical ways. Square both sides. Give it a desk job. Take the x squared, throw it to the other side. What's the curve that we're really looking at? Circle. No more guesswork, right? We're for certain what this is. In fact, it's going to be the unit circle. Okay, now how much of the circle do I want? All of it? Some of it? How am I ever going to figure this out? Endpoints. X ranges between 0 and 1. Are we above the x-axis or are we below it? Above. What's the area of a circle? Pi r squared. What kind of circle do we have? Unit circle. And how much of the unit circle do we want? Quarter of it. Wow. That was quick. That was powerful. Because we know how things work. We know that integration is talking about, at least it could be talking about area under the curve. And I bring that to the discussion, we got that problem solved. Now, to do it geometrically again does mean do it geometrically. Find some kind of shape. And you're looking for shapes that you're accustomed to, such as squares, rectangles, trapezoids, triangles, circles, an ellipse. You guys know what the area is for an ellipse? Let's say if I gave you this equation. X squared over a squared, y squared over b squared equals 1. So there's your ellipse. We can talk about major or minor axes if we want to, but what would be the area? Well, an ellipse is very close to a circle, right? It's very close. In fact, you can say an ellipse is really a generalization of the circle. Okay. In that case, you should see some echoes of the pi r squared inside the area formula for the ellipse. Do you see what we're kind of doing? We're connecting ideas together. And by connecting ideas together, it makes it a whole lot easier to remember things. As opposed to saying, here's this formula, here's this formula, here's this formula, here's this formula. I'll just memorize them all and hope that I get it right. By making these connections, it makes it a whole lot easier to remember what's happening. So you can think of an ellipse again as a circle that you step on, something like that. You can talk about a minor axis is a little shorter. You talk about a major axis a little bit longer. And if they come together where the major axis does equal the minor, you do have a circle. Well, in a nutshell, what happens here is that's the area of an ellipse. pi AB. And like I said a second ago, if the A equals the B, you get pi A squared. And what's the area of a circle again? Right there. Okay, so if I can identify what this shape is, I know some kind of formula for it, you know, we're in probably good shape. Good play on words. Let me throw you this one. Suppose we look at the integration of the absolute value of x plus 1. And let's say it goes between -1 and 2. How am I going to figure this out? Great idea. It has absolute value. I don't like it. Let's just get rid of it. That's a terrible idea. Now, I have an option at this stage. I can do it algebraically. I can do it geometrically. But to do it algebraically, I need some mechanics. I need some kind of formula, something to start linking things together. So the first question is, what's the definition of absolute value? Let's say I want to find the definition for the absolute value of u. How would I express this? What is it? Let me put it to you another way. Let's say I want to find the absolute value of 2. What's that? 2. Okay, I got it. I want to find the absolute value of -2. But why is it 2? That's the answer. Why?
Absolute value denotes distance from 0.
Okay, so the absolute value denotes the distance from 0. Okay, that's a nice geometrical understanding. But I'm looking for something that's mechanical, something that's more algebraic.
Square it and root it.
I don't want to do that. I don't want to square it. So let's go back. The absolute value of 2 is 2. We got that. But how could I make a 2 when all I have at my disposal is a -2? What can I do? Multiply by -1. You take -1, multiply by -2, what do you get? And that's a nice bolt, nut, screw the things together, a nice mechanical approach. So what is the sheer definition of the absolute value of u that we just discovered, or rediscovered? It's going to be u whenever u is non-negative. So it can be 0, it could be positive. I'm just going to take whatever's inside the box and call it good. But in the event which it's negative, whoa, I got to slow down a little bit. It's going to be negative u. Okay, now for this problem, if I'm going to do this algebraically, I have to take the integral and split it apart. Okay, that can be a little bit of a challenge. It's completely doable. And let me just change this up a little bit more. It makes it a little bit more interesting. Let's say -4 to 2. But when x equals -1, I'm right there for the vertex. And what does the absolute value graph look like? Like a V for victory, so something that goes up. When we look at the absolute value function, does it make a little more sense why the graph looks like this? Positive slope, negative slope. You're blending the two graphs together. That's why it's called piecewise. One piece comes with another piece. Well, here I would have to look at not just one function. I'm going to have to look at 2 functions. Because I have a function, this one is not the same as that one. Then I would integrate from, let's say, -4 up to -1. And then from -1 to 2, do it algebraically. Or I can say, ha, I know the secrets. I can do this thing geometrically. I take it, sketch it out, and then I look from -4 to 2, and what I realize is nothing more than two triangles. I find the area for the two triangles, I combine them, add them up, and I find the area under the curve. So for this one, this has a distance of 2, all the way here a distance of 3. We have the function x plus 1, absolute value, drop into 2. So up here, the height's going to be 3. Halfway done. Do it for the next one. -4, -1 has a distance of 3. Take the -4, drop it in, you're going to have this height of 3. In the end, looks like we're going to get 9. Wow. I don't know about you guys, but I would rather do this one geometrically than algebraically. We definitely could. It's just a little more complicated, but it's doable. It really is. So as you go about your integration problems, what this is kind of showing us is you can always just rush into a problem and just keep doing the same thing over and over and over and over again, or you can pause for a second, know how something is actually working, use those ideas, blend them together, and make a problem that seems very complicated a whole lot easier to navigate through. So the choice is really yours. Okay, let me stop there, see if you guys have a question about any of this. Kind of a nice little review from Cal 1. So we talked about some stuff here with integration geometrically, but that really begs the next question about how we can do things more algebraically. And we're going to really explore this for the next few weeks. You know, what if I was going to, first off, just look at something like 2x plus 3, I want to integrate this. And then we take this and we crank it up a little bit more. And let's say we want to integrate the square. Well, this is not too bad. We use the linearity property. We'll have x squared plus 3x. And because it is an indefinite integral, you definitely do not want to forget plus c. Tacking in at the very end. And when you come to this problem, one thing you can possibly do, it will work. You can square this thing out. Because we don't have this multiplicative identity for integrals that you would think that we might have. It's a little different from what you would think of. But we do have this nice linear property where if I take the integrand and express it in terms of summations of these terms of these functions, then we can apply it to different identities that we have. So we could go ahead and apply the binomial theorem. Now the whole entire a plus b, square it, a squared plus 2ab, b squared. We'll have 4x squared, 6x, double it, square the last term, integrate. Then we got a summation between the terms. Use the power rule 3 times. Take it, drop the power down below, crank the power up, drop it down below, and then integration of a constant corresponds to x. And don't forget about the ever elusive plus c. Well, that works. But the next question is what happens when I take this and I crank it up to maybe the 3rd power? Okay, we do something very similar, but then the next question is what happens when I crank it to the 4th power, 5th power, and I crank it up to the 30th power? Yeah, this works, but I don't want to keep doing things the hard way, the old way. I got to figure out how I can do this a little faster, a little more efficient. But to do that, I have to know how things work, because if I don't know how things work, how am I ever going to figure out how to put the pieces back together again to find the problem, to find the solution? Huh, that's interesting. Well, we're going to explore this next time. You guys have a great day, and I'll see you then.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.